An event A, defined on a discrete sample space S, is a subset of S. If the event A consists of only one sample point, then we refer to A as a simple event. There's nothing simpler than one indivisible outcome in an experiment. If, however, the event A consists of two or more sample points, then we refer to A as a compound event. In general, we'll say that an event A occurs on a trial of the experiment if one of the simple events in A occurs. Here's an example. Take the letters of the name Dawn and arrange them at random to form a name or a word, and let A be the event that the middle letter turns out to be an O. What are the simple events here in this event A? They're the points DON and NOD. If either of those occur as a result of this random permutation, we will say that the event A occurred. In example 2, we tossed a coin 3 times. Suppose A is the event that the number of heads is greater than or equal to 1. Let B be the event that the first toss gives us heads. What are the simple events in A itself? Well, the number of heads is greater than or equal to 1 only if we don't obtain all 3 tails. There are 7 such points, HHH, HHT, and so on, and in all of these cases, there's either 1 or 2 or 3 heads. What are the simple events in B, the event that the first toss is heads? In this case, we ensure that the first toss is heads, and we're allowed arbitrary results on tosses 2 and 3. There are 4 points in the event B. If any one of these occurs, we will say that the event B occurs. Definition of a probability distribution. Suppose I have a sample space, a discrete sample space consisting of points A1, A2, A3, and so on. And suppose with the simple event AI, we associate a real number called PAI. These are numbers associated with simple events with the property that they're all non-negative, they're all greater than or equal to 0, they're all less than or equal to 1. But moreover, when I add them all together, the sum is equal to 1. We call this quantity P of AI a probability, and the set of all PAIs is a probability distribution on the sample space S. The events consisting of a single point AI in a sample space we referred to as simple events. For the sample spaces in examples 1 to 3, we will define an appropriate probability distribution. In example 1, for example, S consisted of the 6 permutations of the letters DON. There are 6 points. Any one of them, therefore, could be assigned probability 1/6. For example, AI equals OND would have probability 1/6 in this model. In example 2, we tossed a coin 3 times and recorded the 8 possible outcomes, HHH, HHT, and so on. It makes sense again in this problem to assign probability 1/8 to each of these outcomes. In example 3, we had an infinite number of sample points. In this case, we tossed a coin repeatedly until we obtained 1 tails. We can't possibly assign, in this example, equal probability to every one of these infinite number of points. However, it makes sense, I believe, to assign probability 1/2 to the event tails on the first toss, 1/4 to the event heads followed by tails, 1/8 to the event heads, then tails, and so on. In general, we could assign probability 1/2 to the power n to any event which consists of n-1 heads followed by 1 tail. And indeed, If we add all of these probabilities together, 1/2 plus 1/4 plus 1/8 plus 1/16, and so on, the sum is equal to 1. The probability of an event. Let's suppose A is an event defined on the sample space. In other words, A is some subset of S. The probability of A is the sum of the probabilities corresponding to all of the simple events in A. In other words, we add together over every simple event inside of the composite event A the values of PA. Remember that events consisting of 2 or more points, for example, A1, A2, A3, we refer to as compound events. So, according to this definition, the probability of this event, A, is given by P of A1 plus P of A2 plus P of A3. Note that since I'm adding together non-negative numbers, the probability of any event will be greater than or equal to 0. And since when I add together all possible simple events in the sample space, we end up with 1, then when I add some subset of them, the probability of A will be less than or equal to 1. So this property holds for any event, capital A. Probability of an event. Examples. In example 1, a random experiment consisted of generating one of the 6 random permutations of the letters DON. So the sample space has 6 points in it, the 6 possible permutations. Suppose A is the event that the letters D and O occur together in either of the 2 possible orders. Find the probability of A. Well, we need to list the points in A first, and D and O could occur with D first. So D and O is essentially a unit. N can follow or precede that pair of letters. Or they could occur in order OD with N preceding or following. So there are 4 points in the event A. The probability of A, therefore, is the sum of the probabilities of those 4 points, 1/6 plus 1/6 plus 1/6 plus 1/6, or 4/6, 2/3.
Example 3. In example 3, recall
that the experiment consisted of tossing a coin repeatedly until the first tails occurs. Let's C be the event that the first tail occurs on an odd-numbered toss, for example, on the first toss, or the third, or the fifth, and so on. What's the probability of C? Here the sample space consisted of points like T, HT, HHT, and so on. There could be any number of tosses, heads, followed by a tail. However, the event C is a subset of this, consisting of tails on the first toss, 2 heads and a tail on the third, 4 heads and a tail on the fifth toss, and so on. And so the probability of this event C is the sum of the probabilities of all of the points in C, 1/2, the probability of HHT, which is 1/8, the probability of HHHHT, which is 1/2 to the fifth, and so on. And that's an infinite sequence whose sum is equal to 2/3. A discrete probability model consists of a discrete sample space together with a probability distribution defined on that sample space. In other words, a set of probabilities for each of the simple events in S. We'll refer to this as a discrete probability model. Here's an example. Your roommate, Sloppy Joe, has helped himself to your classic collection of movies on DVD, and most recently, last night in fact, the 4 movies Moulin Rouge, Pirates of the Caribbean, Spider-Man, and Waking Ned Devine. Unfortunately, there are the movies, there are the DVDs. He only puts these DVDs back in their cases when you request he do so, and even then, he does so purely at random. What's the probability that no DVD will end up in the correct case? The sample space, in this case, consists of 4 factorial, or 24 points, the 4 factorial possible permutations of MPSW for Moulin Rouge, Pirates of the Caribbean, Spider-Man, and Waking Ned Devine. Each simple event in this sample space is assumed to have the same probability, 1 over the number of points, 24. Suppose A is the event that no DVD turns out to be in the correct case.
In this case, the correct order of the DVD cases is MPSW. Let's list the points in A such that no DVD ends up in the correct case. In other words, we wish permutations of the letters M, P, S, and W such there's no match between that permutation and the correct order, MPSW. For example, PMWS is a candidate. A in this case has a total of 9 points, so the probability of the set A is 9 over 24, which is 1 over 24 added together 9 times. The probability that no DVD ends up in the correct case is 9 over 24. The probability at least one DVD ends up in the correct case is 1 minus that, which is 15 over 24, or 5/8.
And finally, here is a question, a review question that you can try on your own. 2 fair dice are thrown, and the sum of the numbers on the 2 faces is recorded. And of course, this gives you a value between 2 and 12. Write down an appropriate sample space, define the event that the sum is an even number, and find the probability of that event, P of A. Solution. 2 fair dice have been thrown. There are 36 possible pairs, 1, 1, 1, 2, up to 6, 6. So this constitutes an appropriate sample space for the experiment. We're interested in the event A. The sum is an even number. The points in the event A are 1, 1, 1, 3, 1, 5, up to 6, 6. In other words, they're all pairs for which the sum is an even number. There are 18 such pairs. The probability of A, therefore, is the number of points in A divided by the total number of points in the sample space. 18 divided by 36, which is 1/2.